All right, guys. Good morning. Good morning. One last little bit of practice before our quiz tomorrow in Standard 22 when it comes to using definite integrals to find the areas between two curves. So what I have for us this morning is this example. Find the area of the region bounded by the graphs of 3x cubed minus x squared minus 10x and g of x equals negative x squared plus 2x. So as we've done before, let's go ahead and find the intersections. What are the bounds from left to right for this given region? So where is 3x cubed minus x squared minus 10x equal to negative x squared plus 2x? Let's see here. If I add x squared and subtract 2x, that leaves me 3x cubed. Those cancel out. Minus 12x equal to 0. And I believe I can factor that by factoring a 3x greatest common factor out. Let's see here, giving me x squared minus 4. This will factor into 3x, and x squared minus 4 as a difference of 2 squares becomes x plus 2 quantity x minus 2 equal to 0. So if I set each of these pieces to 0, I should get 3 different intersection points. X equals 0, x equals negative 2, and x equals positive 2. Let's put the negative there. All right, so that's interesting. Usually when I've done these questions in the last couple of classes, I've only gotten 2 intersection points rather than 3. So it might be worthwhile for us to take these 2 functions and graph them just to see what's going on here. Okay, here is our first function. 3x cubed minus x squared minus 10x. Second function was negative x squared plus 2x. All right, so there is an example of what we're looking at. Maybe I'll make the bounds negative 5 to 5 along the x-axis just so we get a better picture. There, that's not bad. So as we found algebraically, these 2 functions intersect at 3 unique points. And x equals negative 2, 0, and 2. The reason that I have 3 intersection points is because there's 2 different regions bounded by the graph. One over here to the left of the y-axis, where our cubic function f of x is on top and our parabola g of x is on bottom. And then vice versa over here to the right, between x equals 0 and 2, where g of x, the parabola, has now become the top function, and f of x, the cubic function, is now located below on bottom. So this is going to require 2 different definite integrals to find the area of each of these 2 regions. And our total area is the sum of those two areas. So first, we're going to have to set up a definite integral from -2 to 0 of f minus g. Minus our second function, negative x squared. Was that plus 2x? And then if I skip ahead a couple slides to give myself some room to work, we'll have to do the second definite integral for the region to the right from 0 to 2 of quantity negative x squared plus 2x minus x cubed minus x squared minus 10x dx. Oops, that would be 3x cubed, pardon me. Notice that on that second definite integral, I had to switch which function came first. G of x is strictly greater than f of x between 0 and 2, where between -2 and 0, f of x is strictly greater than g of x. Let me pause here for some questions. Is there anything that's not making sense as we've gotten these two definite integrals set up? If you have anything, go ahead and speak up. Take yourself off mute. Okay. Let me go back to the first definite integral. And we'll start simplifying. So I'll bring down the definite integral from -2 to 0 of 3x cubed negative x squared minus negative x squared. That's going to cancel out to 0. Negative 10x minus 2x should be a minus 12x dx. We'll need to find the antiderivative and then use fundamental theorem of calculus to simplify. So this should be 3/4 times x to the 4th minus 6x squared to evaluate between -2 and 0. Okay, we'll plug in 0. Well, when I plug in 0, I'm just going to get 0. So 0 minus what I get when I plug in -2. Well, -2 to the 4th should be positive 16. So 3/4 times 16 minus 6 times -2 squared. -2 squared is 4. Let's see here. 0 minus 3/4 of 16, that should be 12. Minus 6 times 4, that should be 24. Zero minus -12 gives me a 12 for region 1 specifically. Of course, we can check that on Desmos. Once again, this is just the area bounded here to the left between x equals -2 and 0. The definite integral from -2 to 0 of quantity f of x minus g of x dx gave us the 12. We're going to combine that 12 with what I get for my next definite integral for the second region on the right-handed side. And as we set that up, I have this definite integral here to work with. So if I simplify the definite integral from 0 to 2 of -3x cubed, once again, -x squared minus -x squared cancels out, and 2x minus -10x becomes a positive 12x. I think this actually was the exact opposite of what we had on the first definite integral. Once I simplify, this should be -3/4 x to the 4th. Once I find the antiderivative, plus 6x squared to evaluate between 0 and +2. Okay, now we'll use fundamental theorem and start evaluating. 2 to the 4th should be 16 still. So I'll have -3/4 times 16 plus 6 times 2 squared, that's 6 times 4. Of course, that would be 24. Minus, well, when I plug in 0 to my antiderivative, that's just going to be 0 again. So simplifying, -3/4 times 16 is -12 plus 24 minus 0. Which is just 12. Of course, we can check that on Desmos, on a graphing calculator. The definite integral from 0 to 2 of g of x minus f of x dx gives us 12 again. The areas of each of these two regions are equal. So if I want to find the total area bounded by these two functions, it should just be 24, 12 plus 12. Good example of one where the two functions create two different regions that we have to combine the total area for. Questions on working through that process, please? Anything that's not making sense so far? Okay, let me go ahead and pull up the practice problems from Standard 22. That's kind of what I wanted to accomplish here this morning. Was there any other particular questions on some of these problems that needed some more explanation here in class this morning?
Can you run through question 9?
Yeah, of course. Number 9 is sine x and cosine 2x between negative pi over 2 and pi over 6. Let me go ahead and write that down. Make sure I got that right here. Sine x, cosine 2x, negative pi over 2 and pi over 6. I think I got that right. Okay. So these should be the bounds for our definite integral. Now I just need to know which function comes first, which one's on top, which one's on bottom. Of course, you could always plug a number in between negative pi over 2 and pi over 6. For example, 0. The sine of 0 is 0. And the cosine of 2 times 0, well, cosine of 0 would be 1. When I graph these here in a second, I should get this function on top and this function on bottom. When I plugged in a test value, such as 0, I got a higher value here than I did here, 1 versus 0. So we're looking at between negative pi over 2, which is here, and pi over 6, which is here. So if I zoom in just a bit, it's basically this region. And as I said, the blue g of x function is strictly greater than sine x, our f of x function, on the interval. So this definite integral should be the definite integral from negative pi over 2 to pi over 6 of cosine 2x minus sine x dx. London, is that making sense so far, getting this set up?
Yeah.
Okay. So the rest is just finding the antiderivative and using fundamental theorem to evaluate. What is the antiderivative of cosine 2x? Well, let's see here. Cosine would have an antiderivative of sine. So this would be sine 2x, but I think I have to have a 1/2 out in front. Let's double check that. The antiderivative of sine 2x is cosine 2x times 2. When I take that last 2 times the 1/2, I just get the cosine 2x that I need up on top. The antiderivative of sine x. Well, the antiderivative of sine would be negative cosine. But I think I need to have, since there's a negative here, plus cosine. Okay, let me check that here. The antiderivative, if I take the derivative of cosine, yep, I get the negative sign that I had here. So that checks out. All right, if you haven't already, it might be good to grab a unit circle because we have to plug in some of these radians values, pi over 6 and pi over 2. So let's see here, 1/2 of sine of 2 times pi over 6. plus the cosine of pi over 6 minus 1/2 of the sine of 2 times 0 is just 0, plus the cosine of 0. Let's see here. If I simplify 2 times pi over 6, that would be pi over 3. And the sine of pi over 3 is root 3 over 2. So 1/2 times square root of 3 over 2. Plus the cosine of pi over 6, that's also root 3 over 2. Minus 1/2 of sine 0, well, that's 0. Plus the cosine of 0, that would be 1. Simplifying further, that would be the square root of 3 over 4. I'm going to convert this to a common denominator so that I can simplify it. Root 3 over 2 becomes 2 root 3 over 4 minus 1. So let's see here. When I simplify and combine these two common denominators, it looks like I would have 3 square root of 3 over 4 minus 1. Or you could call that 3 square root of 3 minus 4 over 4. I can change this 1 to 4/4 and simplify further. Either of these two answers, I'm sure, are fine. Let's double check our work on Desmos. The antiderivative between negative pi over 2 and pi over 6 of quantity g of x minus f of x dx. Okay, I get this about 1.299 decimal approximation. Hopefully 3 square root of 3 minus 4 over 4. I'm off by a value of 1 here. Oh, I gotta plug in negative pi over 2 rather than 0. The sine of negative pi over 2 is negative 1. The cosine of negative pi over 2 is 0, which would change this to minus negative 1 or plus 1. That's a plus 1 there. That's a plus 1 there now, it looks like. Let's see if that fixes our answer. Yep. Oh, no, maybe not. Oh, yeah, I forgot to take it times 1/2. So this would be minus, gosh darn it, what am I doing today? Minus 1/2 times -1. I guess this is why you always check your work. Let's call 1/2 2/4. And now this would be our answer. 3√3 plus 2 over 4. And this will work. Or not. What am I doing here? Let's see here. This would be a +1, but now I need to have a -1. -1/2 times -1 is +1/2, but this extra negative right here makes it back to negative. There we go. Something with that last constant's not making sense.
The answer on Schoology was 3 radical 3 over 4. I don't know if that helps, but
The sine of -π/2. Oh, I need to take that times 2. I see my mistake now, London. Thank you. Too many 2's and negatives floating around. Two times -π/2 is -π. The sine of -π is 0. So this would be 1/2 times 0. Cosine of -π/2 is 0. So essentially, this goes to 0. I've got it now. Thank you for your help, London. It is going to be 3√3 over 4 because now this becomes 0. 2 times negative pi over 2 is going to be negative pi. The sign of negative pi is 0. Cosine of negative pi over 2 is also 0. So essentially, this entire quantity here cancels out to nothing. When I check that here, 3 root 3 over 4 is the answer. Thank you. Got myself confused there, but that's why we check our work, I suppose. Initially, I was plugging in 0 rather than negative pi over 2, just because I'm so used to plugging in 0 sometimes. Was there anything else? Other questions off this practice document? I know that was a tough one, but I can go over anything else if there are questions.
Can we go over number 10?
Mm-hmm. The integrand below of the definite integral is the difference of two functions. Sketch the graph of each function and shade the region whose area is represented by the definite integral. Well, I'm just going to take an assist from Desmos. We have the two functions, x equals 2 minus y, and x equals y squared. Yep. And it would look like between negative 2 and 1 on the y-axis, the region that we're interested in for our area between the two curves is this portion in the middle. Does that help, London?
Yeah, is that all we had to do for that one?
Yep, I think it just said sketch the region.
Okay, perfect.
Yep. The next two on 11 and 12, you have to set up the definite integral on your own and calculate the area between the two functions, two curves. Anything else, guys? Okay, if not, I'll see you guys at 10 o'clock tomorrow morning to take your quiz for Standard 22. Have a good rest of your day. We'll see y'all tomorrow.
You too, thank you.
Yep, you got it. Thanks, guys.
Oh wait, Mr. Hanson.
Yeah, Carson, I'm sorry.
So I've like gone over all the stuff for Standard 23.
Mm-hmm.
When could I take that test?
Whenever you're ready.
Okay.
I think I have a copy of it. Sometime later this week or early next week would be fine. And make sure I have a copy of it ready to go, and we could go from there.
If I'm ready, could I take it tomorrow?
Yeah, let me check my calendar here. I'm gonna stop my screen share. My calendar tomorrow. I have tomorrow afternoon available.
I could do that.
Okay. What time tomorrow afternoon? You gonna do like 2 o'clock?
Yeah, that should work. 2 o'clock.
Okay, I'll send you a calendar invite here in just a second, okay?
Okay, thank you.
No problem, thank you.